Okay, so now that we have the margins of error, we can talk about confidence intervals. So a C confidence interval for the population mean mu would be given by this below. All right, so we're saying a C confidence because that's going to be something like a 95% or 90% or 80%. So that's how we will normally talk about it. So what we're doing here is we're trying to say that our confidence level, that this interval contains the mu value that we're trying to get from the population. So what we're doing is we're taking the x bar, our point estimate, and on one end of the interval, adding the margin of error, on the other end, subtracting the margin of error. Okay, and this was our margin of error calculation before. So that's how we're building this interval. We're taking x bar, our point estimate, and adding and subtracting the margin of error to build an interval. Now the probability that this confidence interval contains mu is C. That's the probability, the confidence level that we're stating. Assuming the estimation process is repeated a large number of times, that's just part of the whole probability of this. So what would go into actually finding a confidence interval? So we would want to verify a few things. In this case, we're talking about sigma being known. So the population standard deviation is known. The sample is random. And then we have one of our two qualifications for the central limit theorem. Either the population is normally distributed or the sample size is at least 30. So the next thing we would do is we would calculate x bar. And that's simply adding up all our sample values and dividing by how many there are. We would find the critical value of z corresponding to whatever particular level of confidence, whether it's 80 or 95 or 99 or whatever. Then we would find the margin of error. And finally, just add and subtract the margin of error from x bar, and that sets up our interval. So looking back at the earlier example, if we wanted to construct a 95% confidence interval, we had figured out that x bar was 21.1, and we figured out that the margin of error was about 0.7. So all we would do is now, for the left endpoint, we take 21.1 and we subtract 0.7, the margin of error, which would give us 20.4. On the other end, at the right endpoint, we would take 21.1, our x bar, and we would add 0.7, the margin of error, giving us 21.8. And that tells us that our interval is from 20.4 to 21.8. So what have we actually found? Well, we're saying that with 95% confidence, the population mean number of hours spent on required athletic activities is between 20.4 and 21.8 hours. So the diagram up here is showing you on a number line what we're talking about. So here is the sample mean, 21.1, and what we've done is we've gone back 0.7 and we've got forward 0.7 to create this interval. All right. Now remember, again, so note, mu is a fixed number. It is either in the confidence interval or not. Mu is not moving around. Okay, it's fixed somewhere, and we're trying to get an interval that contains it. So it's not that there is a 95% probability that the actual mean is in the interval. That's making it sound like the mean is moving. So the correct way is, if a large number of samples is collected and confidence interval is created for each sample, approximately 95% of these intervals will contain mu. So using our approach, 95% of the intervals would contain mu, and that's really what we're talking about with a 95% confidence level. Now, sometimes the case is that you actually want to find what sample size, and in fact, what minimum sample size you should use to ensure a certain margin of error. In other words, we want to fit some specified margin of error. Somebody has given us a margin of error that we have to accomplish. And we actually want to know what the size of a sample that we would need to do that. So basically, we've just reversed this equation here from before. If you remember, we had E equals ZC times sigma over the square root of n. So if we actually solve for n, then we'll get this expression. And so we're just plugging in the critical value of z, the population standard deviation, and the given margin of error. Calculate that, square it, and we get n. Now, since we're talking about sample size, n should be a whole number, so we would round up to the next whole number. In the case where the population standard deviation is unknown, you could use the sample standard deviation if you have a sample with at least size 30. So for example, if we go back to the example from before with the athletes and the number of hours spent on the required activities, if we said, so before we found a margin of error of 0.7, now if we wanted actually a margin of error of 0.5 instead, then we're going to go and figure out how big the sample size needs to be. So going back, we have our 95% confidence, so 0.95 for C. We had our critical value of 1.96. We had the population standard deviation 2.3, and now we're specifying that the margin of error should be 0.5. Plug these in, and we're going to get that the sample size is approximately 81.29, which will round up to 82. So we're saying that we would need at least 82 in our sample in order to guarantee that margin of error. Remember before, it was 40 that was giving us the 0.7. So we need those additional 42 more in our sample to get to this specified margin of error. We could always go with more, but we need at least 82.